Hello to everyone. Today we attend the defense of the thesis of Theo Anot, entitled Terahertz Radiation Confinement Using Metallic Microresonators for Spectroscopy and Manipulation of Single Nanometric Samples, that he realized under the supervision of Romain Peretti and Jean-François Lampin at UMN, and it's in order to obtain the diploma of doctor of the University of Lille. So I will first introduce the members of the jury. So first, the two reviewers, which are Oleg Mitrofanov, that we could not see him, but we say hello to Oleg. Yanko Todorov from Laboratoire de Physique de l'École Normale Supérieure. Then there are the jury member, Giacomo Scalari from ETH Zurich. So Peter Kyung Liu from SUNY at Buffalo is an invited member. Me, I'm Juliette Mangenet from Laboratoire de Physique de l'École Normale Supérieure. And there are the two supervisors, which are Romain Peretti and Jean-François Lampin from UMN. So now, please, Theo, you can start your presentation, and you have about 45 minutes.
Okay. Thank you for the introduction. Good afternoon, everyone. I'm really happy to present to you my work on Terahertz radiation confinement using metallic microresonators for spectroscopy and manipulation of single nanometric samples. So I will begin this presentation by explaining a few words in this title, beginning by the first one, so terahertz. So what is terahertz? Terahertz designate the electromagnetic waves in the frequency range between 100 gigahertz and 10 terahertz.
Sorry, Theo?
Yes?
Could you share it on Zoom? Because we don't see
the
lights.
Il voit pas les slides. Okay. Is it okay? Now?
Thank you.
All right. Thank you. So the terahertz range is at the border between optics and electronics, and due to the lack of sources and detector until recently, it remains one of the least explored part of the electromagnetic spectrum. But with the recent progress it has made in the last 10 years, it has now found a wide range of applications, including in astronomy, telecommunication, security, gas detection, art inspection, or spectroscopy. Here are a few examples of use in astronomy. So maybe you can recognize the two images on the top, which are the cosmic microwave background detected in the terahertz range, which is the first light emitted by the universe. On the far right, you have the first ever recorded picture of a black hole, again at 230 gigahertz, so the terahertz range. And on the bottom, you have an application in art inspection, where terahertz waves are used to detect and observe defects behind a painting without causing any damage. But in my case, I'm mostly interested in the last application, which is spectroscopy. So what is spectroscopy? In optics, it's basically to look at how a sample will reflect, absorb, or transmit different frequency of light. And in the terahertz range, it gives information on how crystal vibrate, about the rotation of gas molecule, or vibration in very large molecules, which are often biomolecules. So on this last point, this brings us to another word in the title, which is nanometric sample, because if we want to study such molecule, such biomolecule, we often have to work with really small sample, because such objects are stuff like proteins, viruses, and all of these kind of sample are usually very small, from a few nanometer to a few micrometer. And this is much smaller than the terahertz wavelengths. which are between 30 micrometer and 3 millimeter. And this kind of sample is often available only in small quantity. So we often don't have a choice but to do the experiment on sub-wavelength sample. Now, the problem in the terahertz range is that existing terahertz sources are usually low power. So for spectroscopy, usually below 100 microwatt. And that the free space focusing is limited to a few tenths of micrometer. So we have very low intensity and almost no interaction with objects smaller than the diffraction limit. So here on the right, you have an example of what kind of equipment you need to generate just 100 milliwatt of continuous terahertz laser. And so this is a laser that we will use a bit later. But anyway, so to enhance the interaction between a terahertz wave and a sub-wavelength sample, one solution is field confinement. So it's used in a wide range of frequency. It can be used for detection, to create nonlinear effect, for ultra-strong coupling, single microparticle spectroscopy, and also for stuff like optical trapping. One way to confine an electric field is to use a waveguide designed for that. So here you have an example of a waveguide that has been designed and tested in our team, which is designed to be broadband and to not introduce dispersion. And with this kind of device, the electromagnetic mode is confined and its cross-section is reduced below the wavelength. So it does increase the intensity locally, but it still has the disadvantage that the light-matter interaction time is still short. So we can do a bit better by using a resonance structure. By putting the sample in the hotspot of a resonance structure, not only do we reduce the confinement volume and the interaction volume, we also increase the interaction time. So here is an example used in the mid-infrared range, where by putting a small amount of a sample in the hotspot of a resonance structure, they could get the spectrum of a low amount of an amino acid here. In the terahertz range, one of the most common resonance structures is the split ring resonator. It's basically a small metallic loop, and it was first introduced in the microwave range for their dispersion properties. And in this context, it's mainly used as a building block for metamaterial, which means you have hundreds or thousands of them assembled together to create an artificial medium with some exotic optical properties. But beside their application in the metamaterial, split ring resonators are also quite adapted to enhance light matter interaction in the terahertz. So they provide a strong electric field confinement with a confinement scale of lambda over 1000. And they have already been demonstrated for use to create nonlinear effect. So here you have an example of electroluminescence induced by terahertz. For ultra-strong coupling, here you have an array of complementary split ring resonator coupled with a 2D electron gas, and they have been used for interaction with sub-wavelength objects. So here on the bottom you have an example where they are used to measure yeast cells. But in all of those applications, it's always done on an array of resonators, so often hundreds or thousands of resonators. So with this method, it's quite possible to detect something. You can detect a shift in the resonance. But it's hard to be quantitative, to extract quantitative information, because each of the split ring resonators, as you can see on the bottom here, each of them is coupled differently to the material you want to analyze. So each of them will have a different response, and when you do a measurement on an array of hundreds of them, you get some sort of blurry average, and you cannot extract precise information. Which is why the experiment must be performed on a single split ring resonator for this application. So this requires a precise modeling of the splittering response in spectroscopy, and most importantly, how this response behave when something is added in the gap. We need to experimentally characterize how it confines the electric field. And finally, we need to perform the actual experiment, which is not that easy, since when I started the thesis, it had never been done before on single resonator in this kind of spectroscopy. So this brings us to the outline of this presentation. So after the end of the introduction, I will start talking about the splittering model and its design. Then I will explain how we will characterize its near field. And finally, we will focus on the low-volume spectroscopy experiment. So before starting the second part, just a brief overview of the experiment to give you a concrete idea of what it looks like. We have a setup based on a commercial equipment where you have a source of light here that is directed on a sample and collected on the other side. So this is here that we put the object we want to analyze, which looks like this in our case, which is a quartz substrate with scattered around a few of this splittering resonator that looks like on the bottom right. So this is only half of the setup in reality, because below the table there is the actual femtosecond laser and all you need to generate the terahertz, and we will come back to that later. So for the splittering model and design, we explain the definition, what we expect as a response, and how to design it for spectroscopy. So what is a splittering resonator, more precisely? So as I said, it's a metallic loop with a gap. And the loop itself behaves as an inductance, while the gap behaves as a capacitor. So overall, it behaves as a LC circuit. And so you have a magnetic field confined around the loop and an electric field confined in the gap. What's interesting about this shape, so 2 points, that the confinement volume can be arbitrarily small, and the capacitance depend on the local permittivity. So we should be able to extract the permittivity from measurement of this resonator. So on the bottom right, you have the simplest possible equivalent circuit, but this is not enough to do spectroscopy since it doesn't have any input or output. So to use it in reality, we need to include the losses and the coupling. So in reality, a resonator is excited by propagative waves, and in return, it loses energy in the form of far-field emission. So that's why we add a few elements to the circuit. We have a voltage source, representing the voltage induced by the external field, and the radiative resistance, which represents the energy lost as radiation. And on top of that, we have, of course, the internal losses, so the regular ohmic losses of a metallic circuit. So now that we've defined the input and output of our system, we can translate that to a quantity that is usable in a transmission in a spectroscopy experiment. So we treat the resonator as a two-port system with one of them being the side of the emitter and the other one being the side of the receiver. And we also have to take into account the intrinsic reflection of the substrate surface. So, yeah. And when we take all of that into account, we end up with this transmission coefficient, where we can recognize the transmission from the interface itself, from the substrate, and the transfer function of the splittering. And in that transfer function, we have the capacitance C that is sensitive to the local permittivity. And so now the last thing we need to take into account are the multiple reflections inside the substrate. They create interferences. And And so, but it can be calculated, and when we do that, this is what we get. So this is a transmission that is normalized by the transmission of the substrate itself. So this is the kind of data that I will present all, over this presentation. And so as you can see, even with this normalization, the thickness of the substrate still has a very strong impact. But it is easy to model, and if we have all the parameters, it should not matter too much. But modulation is with the dispersive material. For example, here I have a material that is modeled by a Lorentz model, so with a resonance. And as you can see on the thinner substrate, 150 micrometer, you can see the behavior that you would expect from two-coupled oscillator. And with the same parameters, but on 1 millimeter, you still have an effect, but as you can see, it's much harder to interpret. But the coupling is actually the same. So now that we have our model, it's time to design the split ring itself, and we want to optimize it for spectroscopy measurement. So the experiment in which we will measure the split ring looks basically like that. So it's only measured and excited in normal incidence with a low numerical aperture, which means that in reality, the split ring will emit, it will scatter light in every direction, and everything that is not in these two cones of light will be lost. So we need to minimize that as much as possible, and that's why we need to study the directivity of the split ring. So to understand how a split ring couples with the outside world, with the propagating waves, the first thing to do is to look at the moments of the dipole moments of the object. Here on the simplest design, you can see that there is two dipole moments. One magnetic dipole moment because of the current in the loop, and one electric dipole moment because of the charge accumulating on each side of the capacitance. So the problem with this magnetic dipole moment is that it's normal to the surface, and the magnetic field of a normally incident beam is orthogonal, is parallel to the surface. So this magnetic field will not interact with the incident beam, and so it's only causing undetected radiative loss. So first change in the design is to cancel it by adding a second loop, and the current in the other loop are in opposite direction. And so with this design, there is no magnetic dipole moment, and we know that it will therefore mostly interact with the electric field. So now that we know that it interacts with the electric field, we can get a more intuitive way to predict what the far-field radiation patterns will look like. So in a conductor, charge carriers are linearly accelerated by an external electric field. And in this structure, it can only happen in the two side branches. So we expect them to behave as at the antenna of the system. And that's why we predict that the far-field emission pattern will look something like that. So this is the emission from two dipole sources. And we have a maximum of emission along the Z, because they are always in phase, no emission along Y, and an emission along X that is slightly attenuated because of the phase shift between them. So like that, we can tune the radiation pattern by moving the branches around. So we tried that we tested that with FDTD simulation. And for the first design, this is the far field we get, which is quite close to what we expected. And if you use this design here, where the branches are much further apart, we should expect the attenuation in X to be stronger. And indeed, this is what we get. So we have higher directivity, which is good. But the problem is that the branches are quite the circuit becomes quite long, and in our application we don't want that because we want to stay in the quasi-static approximation, and we want to be sure the LC circuit model is still correct. And finally, in contrast, this slice design, where there is only one branch, behaves almost like a simple dipole. Finally, the last element of the design are the quality factor and the confinement volume. Both of them are adjusted with the shape of the gap. So using a large capacitance like that reduces the resonance frequency, which is proportional to the square root, 1 over square root of LC. So when you do that, the antenna becomes smaller relative to the wavelength of resonance, and therefore there is less coupling with the far field, and we get a higher quality factor. And finally, if we want to change the confinement volume without changing the capacitance, we can simply use this kind of design where the ratio between the surface area of the capacitance and this distance stay constant. So now that we have all the elements of the design, we can fabricate them. So we do that on, they are fabricated in gold on a quartz substrate, and we could get a very good conformity with the desired shape and a very good aspect ratio. So here we were able to reach a gap size down to about 25 nanometer. So now the split ring are ready for testing. We have a design that allows us to control the quality factor, confinement volume, and directivity. And we have a model to compare our measurement with, and we've fabricated the split ring resonator. So now we will characterize them, and starting with near-field characterization. So we'll explain here near-field microscopy, the result we got, and how to interpret them. So why do we need experimental measurement of the spatial distribution? So this is because all these applications about near-field electric field confinement, they all rely heavily on the field spatial distribution. And at this scale, any defect on the fabrication could strongly impact this field distribution. So we need a way to experimentally characterize it to know how it will couple with a material. So for that, we investigated how to use scanning near-field optical microscope, so SNOM, to do that. So here are the main elements of such a microscope. We have a source of light, which can be a lot of things, but here we will use a gas laser, so a fixed frequency. So this is the laser I showed in the introduction, but not important. So this is sent in a Michelson interferometer, and this is focused on an AFM probe with a parabolic mirror. So what is the AFM stage? You have a very sharp tip that will scan the sample, and this tip will scatter the light from the laser here. And how it scatters this light strongly depends on the optical property of the material right below the tip. So when you do this scan, you get information at a sub-wavelength scale on your object. Additionally, you have a system of tip oscillation that allows you to remove all the background signal by looking at the harmonics of this tip frequency. So the plan here is to look at the split ring, a split ring that is in tune with our terahertz source, so at 2.5 terahertz. And if we model the SNOM tip as a dipole antenna, which is polarized by a strong electric field on its apex, we expect the scattering to scale with the mode profile of the split ring resonator. So here on the top right, you have the simulated field profile, which is directly in the plane of the split ring. But this is not exactly what we expect. We will be scanning above the split ring. This, in the bottom right, is the expected image. So this is the the field intensity normal to the surface in a plane just above the split-ring resonator. So we proceed to the experiment, and this is our result. Here, on the left, just for comparison, this is the measurement on the split ring that is not in tune with our source. And as you can see almost nothing. You see a bit of difference between the gold and the substrate, but that's it. And in the tuned one, you can see there is a clear effect in the gap with a very bright spot. So the good news is there is a clear effect of the resonance on the image, and which confirms of some field concentration inside the gap. But of course, there is a problem of asymmetry in this image. And a bigger problem is that this asymmetry as a field profile is not physically possible because it doesn't respect the right symmetry rules. So we attributed this asymmetry to a modification of the far field pattern depending on the probe position on the sample. So this is basically the idea. As I said, the AFM stage is coupled to the laser with a parabolic mirror, which is not center. So we have an intrinsic asymmetry in this setup. And this system formed by the split ring and the antenna, they form a complex system, a complex antenna. And our hypothesis is that the directive of this system change with the position of the probe, which affect, in the end, the coupling and the signal. So to test this hypothesis, we performed simulation, FDTC simulation here of the system represented on the right here, where you have a long 70 micrometer metallic tip on top of a split ring. And this simulation is repeated for 20 positions of the probe along this axis, and for each of them, 4 positions along the vertical axis. And for each of these simulations, we compute the far field radiation pattern of the whole system. And at the end, with the 4 vertical positions, we can extract the second harmonic demodulated signal, which is what we measured in the previous image. So when we look at the different radiation pattern, it confirms the anisotropy. So as you can see, when we compute the far field pattern of just a split ring alone, it's as expected symmetrical. But when we add the probe on one side, it becomes asymmetric, and the radiation is directed away from the probe. So with all the simulation, we extracted the signal. And so this is the line along which we computed the signal. And as you can see on the right, there is a pretty good agreement between this simulation and the measurement. So in the end, we finally confirmed that the split ring resonator does behave as in the simulation. So to conclude this part, we've determined that the interpretation of a SNOM image is not straightforward, yet we could confirm the field confinement in the gap. And we've established that this SNOM design is highly anisotropic and is not adapted to give a reliable image of such a metallic structure. And maybe there could be a more adapted structure, such as excitation with a gas gram microscope or attenuated total internal reflection. So with the field confinement confirmed, we attack the last point, which is the actual experiment on low volume spectroscopy. So we'll start by presenting the time domain spectroscopy, then an error correction, and finally the single split ring resonator spectroscopy. So time domain spectroscopy is one of the most widely used methods of spectroscopy in the terahertz range. The main elements are represented here. You have a femtosecond laser that is divided in 2 beams. So each pulse is divided in 2. the first pulse goes directly to the emission antenna, and the other one goes through the delay line and to a receiver antenna. On the emission side, the femtosecond pulse is converted in a terahertz pulse through optical rectification. And on the detector side, the terahertz pulse is measured with photoconductive sampling. And this photoconductive sampling gives you 1 point in the time trace. And by moving the delay line, by scanning the delay line, we can reconstruct the complete pulse. So in our TDS setup, this is this is a typical pulse that we can measure. So as you can see in the time domain, we have a very short and therefore broadband pulse. And we switch to the frequency domain with a simple Fourier transform. And as you can see, it provides us a very high dynamic range, over 90 dB, and over a wide range of frequency here, almost 6 terahertz. So how to use TDS to extract properties from a sub-wavelength sample? So the plan of the experiment would be to put a bit of this sample on a split ring resonator. Then we focus our terahertz beam on the split ring in a nitrogen purge box to avoid water absorption. And finally, we use the analytical model to fit the transmission and get the sample properties. Of course, in this, there is a lot of parameters to extract. So we need to split the work to make it work. So in reality, there is 4 transmission measurements. 1 transmission through air, 1 transmission just through the substrate, another one with only the split ring on the substrate, and finally the measurement with the split ring coupled with the material. With the first 2 measurements, air and substrate, we get all the substrate properties. Then with the measurement on substrate and the split ring, we get all the split ring properties. And finally, with the split ring coupled compared to the substrate and all the information we gathered in the previous experiment, we finally get the material permittivity. So this is the plan, but all of this is based on the assumption that we are able to detect a single split ring resonator. And this is not obvious since until very recently, in 2022, it had never been done before in time domain spectroscopy. So inspired by this first measurement that I mentioned, we started by testing complementary split ring resonator, which means a full plane of gold with just an aperture in the shape of a split ring, which should give us the same intensity of signal. And so this is our first experiment, and we were able to detect the resonance from this split ring. And so with that, we confirmed that the dynamic range of the TDS is high enough to detect the signal from a single resonator. The problem with regular split ring resonator is that we don't want to detect only a small signal, but we want to detect a small variation in a large signal. And with the strong signal come other sources of noise. Indeed, the noise is mostly defined in terms of dynamic range. And so the dynamic range is just defined as the difference between, or the ratio between the maximum of signal and the noise you have at high frequency or when the beam is blocked. So it only considers the dark noise, and it does not render any noise source that comes directly from the signal. So to study this kind of noise, we take advantage of the fact that when you record a terahertz signal, you usually take thousands of time traces and average them all together. So we can record all of this of the individual traces and do a bit of statistic on them to analyze the noise. And here we define the noise as the standard variation of the signal. And when we do that, you can see that the standard deviation is not flat at all, and it's strongly correlated with the signal. You can see in the time domain and in the frequency domain. And it seems to be proportional to the derivative of the signal. So where does this noise come from? When we look at the individual time traces, if we look closely, we can notice that there is a slight drift, a slight delay between each of the traces, which causes this noise. And the problem with this kind of error is that averaging shifted trace does not just add some noise that you could remove by averaging more traces. In fact, it's always remove energy from the system. So it is not any noise, it is a biased noise. And what that means is that, first of all, the difference between the measured signal and what I would call the true signal can be much higher than the standard deviation. And the worst is that the accuracy tends to decrease with the number of traces. But the good news about this kind of error is that it can be corrected. So to do that, we record, again, each trace individually. We realign them, and then we do the average. And as you can see, here you have in blue the standard deviation before correction, and then in red after correction. And you can see that this correction almost completely removes the correlation between the signal and the standard deviation. So what are the concrete consequences on a terahertz signal? Well, to visualize them, here I plotted the measured delay between each traces in two different measurements. Both of them are on 10,000 traces, which takes about 25 minutes, which is not actually very long, but still you can see that from one measurement to another, the delay drift can be very different. Sometimes it's just about one time step, so 30 femtosecond. And the drift can be much higher. It can reach more than 3 time step. And when this happened, it has huge consequences on the signal. Here on the right, you can see two signals that are actually from the exact same data. The blue one is before correction, and as you can see, it could very easily be interpreted as losses at high frequency. And the red one is after correction. So this, there is actually no particular losses at high frequency in this signal. So we identified two kinds of delay. We have a jitter that is usually the same on every measurement, and most importantly, a large drift, which can be very different this time between every measurement that we assume to be due to the temperature drift in the optical fibers. So with the signal corrected, we went to the actual experiment. So the first thing we wanted to do was to demonstrate that we were indeed able to detect single spectrum resonator. So we did the test on a lot of them. Well, not that much, here 7 of them, on a wide range of frequency. And as you can see, these are the very first spectrum of single spectrum resonator. And on all of them, you can clearly identify the resonance, and this is true from here 250 gigahertz up to 3 terahertz. And the shape of this resonance is similar to the one we predicted, at least as long as the quasi-static approximation is correct, which usually breaks at about twice the resonance frequency. So we also try to verify what I said at the beginning about the quality factor. So I said that using this kind of shape would result in a higher quality factor. And so we tried this one to test our model. And as you can see, we were able to feed the data reasonably well. And we could measure a quality factor of almost 30, which is, to my knowledge, one of the highest quality factor on this kind of splitting resonator alone at room temperature. Now, since our model and our split ring resonator are working, we will use glutamic acid as a test sample to test if we are able to extract information from a sample. So this is a common amino acid. It has a strong resonance at 1.2 terahertz, which we are interested in here. With this kind of resonance, we should expect even to reach the strong coupling regime between our split ring and the material. This material easily crystallized from a saturated solution, and it's completely safe to handle. The only disadvantage is that it's anisotropic, so there is a few parameters that are not really comparable between the measurement on a pellet compared to a measurement on potentially a single crystal. So just as a reminder of the expected shape, this is the simulation on the result of the model that I showed at the beginning. Here it's for 1 millimeter substrate we used for this experiment. And yeah, this is the appearance of the spectrum we expect. And yeah, so this is results from last week. So we were able to, we fabricated 16 isolated split ring. We measured them and then deposited some glutamic acid. And after that, 2 of them happened to have their resonance still close to 1.2 terahertz, so with the glutamic acid. And here you have what the crystals looks like, and below this little agglomeration, you have a split ring. So this was the spectrum before we put the glutamic acid. So it's a bit, it's not perfect. You can see there is some water absorption line, but we are still able to get the resonance, and we are also able to fit it with our model. And on the right, with a lot more oscillation due to the Fabry-Perot, you have the transmission with the glutamic acid. And even if the effect, it can be complicated to interpret the spectrum, you can see that we are still able to fit it reasonably well. And this is the second one, so same thing. This time, the experiment on a pellet. And the other one are the 2 split ring resonator. And as you can see, for the frequency of the mode and the bandwidths, the results are very encouraging. And yeah, we were able to get a value that is pretty close to the reality. For the oscillator strength and the permittivity at high frequency, this is not as good, I would say, but we have to keep in mind that those parameters are potentially affected by the anisotropy, so the actual value is not really known for the moment. And there might also be some cross-correlation between the last 3 parameters, so those 2, and what I call the filling factor, which is just a phenomenological parameters to represent how much of the gap is actually filled with glutamic acid. So for the moment, there is no good way to know if this is a problem in the measurement or if this is due to anisotropy. Now with the parameter extracted, we can get a much clearer idea of the spectrum by looking at the transmission coefficient without the Fabry-Perot. So for that, we take all the parameters and we apply them to a system where there is only one interface, so no reflection inside the substrate, and this is the spectrum we get. And as you can see, there is some, especially on the right, some beginning of splitting action. So we are not right now in the strong coupling regime, but considering that the coupling here was not ideal, we can do much better, and I think the coupling regime is strong coupling regime is accessible in this configuration. So we showed that spectroscopy with a single splitting resonator is possible. For that, we corrected a major source of error in TDS. We measured a single splitting resonator over more than a decade of frequency, and we validated our model and design, and were able to reach high quality factor. And in the process, we extracted resonance parameter from an extremely low amount of glutamic acid, estimated about 20 picogram or 15 femtoliter. So finally, I will conclude with a brief summary of what was achieved here. We developed an analytical model for a splitting resonator coupled to a sample material. We performed the first splitting resonator mode imaging with terahertz norm. We developed a method of TDS error correction. We performed single resonator spectroscopy. And finally, we extracted resonance parameters from a measurement on a splitting resonator from a very low amount of glutamic acid. The impact of this work on the various subjects aborded are, so for the SNOM, so again, we generated the first SNOM image of a terrestrial photonic mode, and I believe we contributed to the general understanding of this kind of a microscopy. For the error correction, this is probably it could be the biggest impact, since as we saw, this kind of error could really be a huge source of mistake in a very large variety of experiments. And finally, for spectroscopy resonator, we went from simple detection to measurement. The next improvement in this experiment are on all those points. The analytical model first could be still improved and refined by looking more closely in the description of the radiative losses, which is imperfect right now. For the coupling between the splitting and the sample, it could the reproducibility could be greatly increased by using this kind of picoliter dispenser and doing that under controlled humidity and temperature. And for the TDS experiment itself, of course, since this is only from last week, we need to repeat them. And if we need more signal-to-noise ratio, current recent TDS setup provides a much even better signal. So I showed you at the beginning up to 6 terahertz. Here this is a signal measured from a commercial setup. And in the same time, we were able to get signal up to 8 terahertz. And finally, and this is probably the most important improvement for this project, is to continue in the domain of noise analysis and define rigorously error bar applicable to time domain spectroscopy, which would be the only way, and it should be completely necessary to trust any parameter that we extract from our measurement. So here, for example, I talked about the oscillator strength that we could not know if it was because of our measurement or because of the anisotropy. Defining an error bar is the only way to know for sure if we can trust our measurement. So on that, I thank you for your attention.
So, thank you for this presentation. So it's time for discussion with the jury members. I will now give the floor to the reviewer. So I propose to start with Oleg, who is quite far from us, but I don't see him. Oleg, yeah. Do you hear us?
You're muted, Oleg.
Ah, okay. So, so Oleg, are you there? So it's time for discussion, and I start with the reviewer, and I propose that Oleg starts his comment and question on the work. Oleg, do you hear us? C'est un peu difficile.
Is your microphone activated?
Les liens optiques dans l'Atlantique. France et les États-Unis.
D'habitude, on a mis le son là.
Pour les questions, est-ce qu'on pourrait mettre les
Is it working now?
Ah.
Can you hear me now?
Yes.
Yeah.
Yes, all right. Sorry. I've got to say, first of all, well, I enjoyed very much the presentation. So this is the first time I'm doing sort of feedback to defense and funds, so I'm not entirely sure what's the procedure and what kind of comments I'm supposed to be giving. But I've got to say that I was very impressed with the work that you've done. I appreciate it. It's also very very difficult and time-consuming work, and it's pretty impressive. I think I was quite really interested in the fact that you found with the scattering that goes into, that is affected by the presence of a tip. It's something that I think it's being really underestimated in the community, and I think it's very interesting result. I also was very much impressed with the your analysis of the spectroscopy and how you can improve basically the sensitivity of the technique by applying this shifting of the time domain signal and sort of realizing where the error is coming from. I think those is also very good work. Juliette, am I supposed to be asking also questions about some of the work?
Yes, you should.
Okay, very good. So if I come back to the this identification of the scattering by the tip. So what I wanted to ask is, when you were discussing the system, you mentioned the system is basically microsemantic parameter. So the signal would be, I imagine, would be very much dependent also on the position of sort of the mirror, right?
Yeah.
So the information that you've shown mostly just says about, well, this is the signal I've been measuring. So I wonder if you could say something about the effect of the phase, that you probably should also expect some impact on images. And the sort of related question to this, of those resonators, right? When you have the suppression of the signal by the fact that you have a tip, right? Let's say, for example, the tip is part of the lower part of that, of the split ring. The suppression indicates, okay, well, we expect to see a small signal. But if I look at the image, there's also, I mean, it kind of goes below the level of the signal that you could measure on the substrate. So I wonder if you could explain the reason sort of for this effect. I can see it's modeled, I mean, in your modeling, it agrees with your experiments, but I wonder if how can you interpret the fact that it actually goes below the level of the signal on the substrate?
Okay, thank you for the question. So for the phase effect on the signal, when we are in a homodyne detection, so what we are measuring is actually a product of a phase modulation and an amplitude modulation because of the interference, the interference with the reference arms, and actually most of this signal seems to be mostly from the phase because when we do the experiment without the reference arm, we are not able to get any signal. So when we remove the phase modulation, we don't see anything at all. So yeah, clearly the phase modulation has a strong impact on this image. Now, if the phase modulation, if the problem of the asymmetry was only from this phase modulation, we should expect, depending on the length of the reference arm, to have sometimes a bright spot on the upper arms and sometimes a bright spot on the lower arms. And this is something that we never observed. So no matter how, if each time we had signal, it was always in this configuration. And yes, about the intensity of the signal being lower than the substrate. So first of all, if we go back to the radiation pattern, you can see that it really decreases the signal compared to, I mean, if you look at the opposite direction, here at about 45 degrees, the signal strongly decreases compared to when there is no tip at all. And this is something, it is an effect that you should not expect only with the substrate. So here I only talked about the signal that is scattered directly from the near electric field of the structure, but you can also, of course, use NOM to study materials. So you have some signal that comes from the material itself, from the substrate or from the gold, and there is no reason to assume that you will detect this signal when you are on the gold on the directly on the resonator. So you when you are on the gold on the gold tip and the radiation pattern is not toward the parabolic mirror, you do not detect the signal from the substrate itself. So I don't think there is a reason to assume that this signal level would be the minimum. So I don't know if I answered your question.
Yes. I think, but can I just maybe follow up a little bit? So when you're measuring the phase modulation, how is that actually done in experimentally? I mean, obviously, the waveruns in terahertz is fairly long, and I think in some cases, doing the phase modulation in the same way as people do, for example, in optical or even in the infrared is much more difficult. So I wonder how was it done in your system?
So we are only in homodyne detection. We tried pseudo-heterodyne, where the reference arm is modulated, but we could not get indeed we could not get enough modulation in the vibration of this reference mirror. So actually, we were not able to completely to get a correct pseudo-heterodyne measurement, and so what we get is a mix. It's only the product, and we were not able, unfortunately, to isolate the phase modulation and the product. We can only assume that it's mostly because of the phase, because we don't see anything without the reference arm, but we were not able to isolate them.
So maybe just to clarify, so you would set a delay at a particular position and then do the two-dimensional scanning without moving any delay of the mirror. Is
Yes,
that right?
yes. We select the delay that gives us a good signal. Yeah.
And no matter how you choose the delay, it always gives this
Yes.
strongest signal on the closest part and the lower signal when what can be actually the other way around.
Actually
Right.
Exactly.
Yeah. Okay. That's very interesting. You answered the question very well. Thank you. Julia, do we just kind of move on to somebody else? Or
No, you can put a few another question, perhaps. I don't know. You have a few times. If you have another question, if you want, usually you can ask up to 4 questions about. Depends on.
I'm happy maybe to let somebody else, and then maybe I'll come back to the questions again.
Okay, so we will see. Okay, so thank you. So we will continue. I will give the floor to Janko. So please, Janko.
Okay, I'm supposed to.
It's one.
Okay, so first of all, I would like really to congratulate you on this work, which is extremely complete. You showed, with respect to the manuscript, actually, which, by the way, was very clear and very pleasant to read. You showed only a few results, and you have much more development. And I think that what we saw today is really this capacity to build. Not only to build original experimental setups, but also to basically to analyze the data and to perform a very advanced data treatment. Especially in this case, you put into place this algorithm to remove the noise, much of the noise of the TDA system, which I think it's really important and puts your group on the forward, let's say, worldwide forward place in this type of measurements. And really the measurements on the single resonator that you showed are truly quite impressive. I think I would like to underline also that something that you did not show is that you also fabricated these samples. You took active part of the fabrication, and also something which is also important is to combine different materials, basically organic materials, with these metallic nanostructures. And we could clearly see in the manuscript that there are some issues that were not obvious from the beginning, and you really was very successful in solving them. So I have a few questions. Basically, I will follow maybe the logic of the manuscript. So in the first part, you describe analytical model actually of a lumped RLC resonator, which interacts with the incident wave through the couple mode theory. Well, a very, very general question when we work on this type of model is basically define some capacitances, some inductances. And I did not find actually, did you try to relate the actual value of these capacitances or the inductances on the geometry of the resonators?
I did try, but it didn't lead to a very conclusive result because there is a lot of parameters that are a bit difficult to model at this scale. So, in particular, the inductance, it's usually very dependent on the shape, the corner of the metal, and all of that will bring this further to the simulation. And most importantly, I would say, in the measurement at the end, you can only get, if you just have the resonator, in the circuit it's defined by 3 parameters, resistance, inductance, capacitance. But in the end, in what you can measure, you only have 2, which are the resonance frequency and damping rate. And so the problem with, so you cannot really extract for sure the 3. You can only have the product and difference. So yeah, that's why I did not try too much in this direction, because for the moment there is no real way to test them experimentally.
Okay, so it's really an effective model that gives you some resonance, the position of the resonance, and still, if you go to page 18 of your presentation, where you show schematics of the coupling, basically you say that you say, okay, so you have an equivalent circuit for an incident wave, let's say, which interacts with the your system, and you basically put these all the elements in series.
Yes.
And what not in parallel? I mean, or it's something which justifies that choice. Do you have?
So for first of all, for the internal losses, so it's the simplest one. They are supposed to be proportional to the current, so that's the only way to put them. But if indeed, for the radiative resistance in particular, the choice is absolutely not obvious. So there is 2 reasons for placing it there for the moment, at least. First of all, it's the definition of radiative resistance. It's a concept that is used for antennas, and the definition of this radiation resistance is actually in series. So that the first guess was to just follow what was done in the antenna, but actually we noticed that there was some inconsistency because of that. So first of all, in this model, the radiative resistance are proportional to the current, but the problem is in a real antenna, we would mostly expect them to scale with the derivative of the current. So it could make more physical sense to put it in parallel with the inductance. And in fact, this is also what we observed with the problem of modeling the quality factor. When we change parameter in FDTD simulation, it appears that having the losses in R over L, like in this circuit, is not really consistent with all our simulation, and it would probably make more sense to have radiative losses in the form of 1 over RC. But the problem with that in the simulation, when you do that, not in simulation, but for the analytical model, when you do that, you can no longer separate clearly the radiative losses from the internal losses. So here in this model, you have 2 separate dumping rates that you can treat independently. and then you add them together. But I agree that it would probably make, and this is actually what I mean when I say that the analytical model needs to be refined. This is about this point especially. So all the theories that I use, for example, to take into account the transmission, the reflection on the substrate. So it was based on the work of Fan and with time domain coupled mode theory, and the possibility to separate the radiative resistance from the ohmic resistance is one of the requirements for this theory to work. So it could probably be better with a more refined circuit, but for that we will need to go back further in the calculation to.
Okay, thank you. Maybe in slide 26, something I did not quite understood is when you basically define the 26. It's the next one, I think.
Sorry.
Yeah, when you basically you speak about confinement volume while keep a constant capacitance with the ratio H over G constant. How do you justify that? Because the capacitance is actually, I mean, I would expect that in this configuration you have a very big number, I mean, it's very strong fringing fields, which will actually determine your capacitance. I would rather say that you have a slot capacitance rather than planar one.
Yes. So to model the capacitance, there is two limits that we can look at. The first one is when the gap side is much smaller than the thickness. Then it looks pretty much like a parallel plate capacitance. And in that case, the capacitance is proportional to this ratio. So since we don't change the thickness, this value is directly proportional to the surface area of the plate. And in the other extreme, when the thickness is much smaller than the gap, then the charges are not accumulating actually only at the surface, but mostly in this area, which is also defined with the fringing field indeed. But the surface of this field here is also proportional to this width A. So in both cases, we still have this relation. And most importantly, perhaps, in practice, when we fabricated them in array first, a lot of these shapes, and we could detect almost no change in the resonance frequency.
Okay, look, I'm not 100% convinced by I would expect some logarithmic contribution parabolic functions, but that's okay. In any case, it's well, I guess my feeling is that you don't. It's not so important for the.
Yes, I think.
For the future. Okay, maybe if we could move to the next. So then I also would like to congratulate you really for these studies with scanning probe, which in terahertz is really not. I guess not easy to do this, and you have a very nice interpretation of the results. Namely, you at some point you really explain this phenomena as a convolution between the radiative field of the tip, right, with the near field of the nanostructure. So by looking actually at formula 3.8 in your manuscript, probably you don't remember it, but I mean, one could think that if you know very well let's say the emission pattern of the tip, is it possible somehow to invert this field map and to numerically retrieve
I guess
the actual...
the problem is I don't know any other way to compute this far field pattern, or other than doing the full simulation. So at the end, if you have to do all the simulation and base your measurement on that, I think it can become pretty circular. But
it will not be.
I think it's possible, but I don't know how we could analytically predict this sample. So.
Okay, and also I think that the tip that you employ in this experiment is all metallic, if I'm not.
It's silicon coated in platinum.
Okay, silicon, and the coating is like going along all the.
I'm not. But what I said about the emission is also true about the excitation. So you would still have an asymmetry. But yeah, it would be reduced, and that's also. But ideally, you would want to have both the excitation and the measurement that are isotropic, which is why we investigated the heterogeneity total internal reflection.
But in the transmission experiment, one might argue that you can position the tip really perpendicular to the structure and have really high symmetry. And
yes, but actually in the simulation, the tip is perfectly perpendicular.
Ah, okay.
And the symmetry comes from the fact that it's not in the middle. It's on one branch or the other.
Okay. And then, do you think that this technique also can be applied? I mean, you use later on split ring resonators and you look through the transmission. Do you think that you can also use it to probe the glutamic acid, for example, directly?
Directly?
With this technique?
Yes, it's probably possible. Well, you would have to get the same kind of information, you would have to do something spectrally resolved, which is not our case here. Our source is a gas laser, and I don't know what kind of the usual power of the sources used for spectrally resolved SNOM, but I don't think it's as high.
Okay.
But yeah, in theory, it's possible.
I also had, of course, many questions about the measurements with the single split rings. Simply, I cannot retrieve them in my notes. But still, one question is, I mean, when you look at the spectra that you have with a single split ring resonator, it's you see always a kind of sometimes a small asymmetry, yes, which is quite systematic actually. So this comes from the Fabry-Perot effect of the substrate, or it's
yes,
something?
This is the kind of asymmetry we expect because of the interferences. Well, here with 1 millimeter, it's quite extreme, but you can still see that this one is already quite asymmetric, even though. So yeah, we attribute it to that.
Okay, and so in the measurements with the glutamic acid, for example, in the one that you show, it's a very nice experiment where you show the transmission. Before moving to that question, another. Sorry. Let's stay a little bit on the single resonators.
Yes.
Okay. So, for example, it is in principle possible if you push a little bit the Kaplan theory, you can relate the contrast to the ratio between the radiation and non-radiation loss. Actually, and typically, I think, I mean, I guess you're very undercoupled, so I would say that your radiation loss here is maybe you have 0.5% of contrast.
Yes.
So 95%, I would say, it's non-radiation loss. Is that?
When we extract the coupling constant, the decay rate, so that's when we separate both of them, the non-radiative decay rate is in the order of 10 to the power 10 to the minus 11 second inverse second. Mm-hmm. And for the so that was the non-radiative loss, and the radiative loss are fitted at about 10 to the minus 8. The problem with this separation is the problem of the directivity, because in theory you have clearly separated internal loss and external losses. But in this model, the external losses that you do not detect, they will end up in the model, in the fit. They will be interpreted as the internal loss. There is no way to separate the radiative losses that you don't detect from the internal losses with the current model.
But okay, maybe we can talk about this, because in principle in Kappa-Mott theory you can have a relationship. I mean, you have two parameters, which is the contrast of the dip and the line width.
But in tandem and Kappa-Mott theory, you have 2 ports, and you assume that everything goes through those 2 ports, and everything else is just losses.
Ah, okay. So
but here what we should do maybe is to have a 3rd port, which represents everything that just goes away and is not detected.
Ah, okay, I see. But okay. So you mean that the contrast of these resonances is not exactly, does not have a clear relationship, let's say, with the, okay. By the way, in this set of data, it would be, I mean, I think it would be interesting to put a graph where you put the frequency, the quality factors, but maybe not the contrast. It has not clear meaning as a function of the size of the, so it's to see. And what we can see that there is a systematic increase of the line width, right, as a function of the, when actually the, well, what was this number of 15.5? This is the size of the loop, right?
This is the size of the square.
The size of the square, okay. As a function of the size of the square, you can see that there is some systematic change of the line width. Do you think that there is a clear interpretation of this phenomenon?
I did notice that for the very lower one, but not so much for the other. I'm not sure.
Well, maybe it's something that can be investigated further. Okay, so maybe now if you come back, and then I will not maybe take too much time. Madam President, what do you?
You feel free.
Okay. In any case, I lost my. I think Jean-François maybe took my questions to cut. So, no, I'm just kidding. So, if we come to the coupling of the resonator with the single resonator with the glutamic acid, how is the very nice question? So you see these are crystals, right?
Yes.
And they sit on the top of the split ring, so they not actually fill the gap.
Yes.
So you're mostly coupled, let's say, to the fringing fields of the resonator, okay?
Yeah.
And that maybe it's a reason to decrease the absorption feature. So.
So this was. This is the reason why this split ring is thinner than the one. So I didn't mention that, but this is 200 nanometer thick, while the previous one were 500 nanometer. And yeah, the goal for that is to have a thickness that is smaller than the gap, so that most of the capacitance would come from the fringing field. So actually, because the thickness is quite small, the parallel plates capacitance contribution is smaller.
Okay, so you also mentioned some randomness in the orientation of the dipoles that couple with. So these films actually they homogeneous, locally homogeneous, or there is some inhomogeneity, or
for the crystals?
Yes.
I don't know yet. That would require for this one, probably not.
Okay, I see. No, because I'm asking this because, of course, you can. I think for this wavelength range, you can neglect the diffusion probably because much more than the wavelength. But still, you might. I'd be wondering your opinion. I mean, if you have some inhomogeneous material, then you excite locally a dipole. And then this excitation also depends on what is around, like a Clausius-Mosotty-like effect. And do you think that, for example, having this, let's say, random surrounding of the inside the crystal can also contribute to some enlargement or decrease of the response that you expect?
Yes, I would say that's possible. And in fact, one of the main interest about this experiment. Unfortunately, in this picture, we did not succeed. But the goal is to perform experiment on single crystal, if that's possible. You can see that some of the crystals are absolutely large enough to fill the capacitance by themselves. So yes, I agree, and I think that's why one of the reasons why it would be interesting to get a bit better at controlling the crystallization. To get only to remove this effect and get only single crystals. Okay,
and maybe when you in one of the next slide, I think you show spectra which are free from these Fabry-Perot oscillations.
Yes,
I think yes. Okay, here. So question here: can you? Where is the resonance of the glutamic acid? I mean, can you superimpose this with the, let's say, spectrum of a split ring, a single split ring, or the split ring before you cover it?
The single split ring will be just a very nice Lorentzian shape at a bit higher frequency, but not that high like here probably, because they are not that coupled, they are not that well coupled. And yeah, the glutamic acid is about at 1.2.
So, wait a minute. So you say that you have like the split ring at 1.3?
Before the glutamic acid,
okay.
Yes.
And then, so there is another effect which is a shift.
Yes, because the average
that was not
is higher than 1.
Okay. Well, which is already quite... no, I think it would be interesting to put this response of a, let's say, uncoated split ring to see the exact effect of the... of the sample, which is probably not only a change in the
so here you can see it's at 1.3.
Okay.
And it's shifted at lower frequency.
It's shifted and okay, and also the contrast.
Yeah, it gets wider.
The contrast is not so affected, I would say, because you have it's going from down to 0.985.
Yes.
So you keep almost the same contrast, but you shift.
It's difficult to judge the contrast because of the Fabry-Perot that came back, because most you will need to filter that to get a precise value.
Okay. But then the following question is, if you go to 56. How do you define then the Rabi splitting? Because your resonance is not matched anymore. I mean, no? In 57, sorry.
Yes.
Where do you see?
So this is just an estimation based on the extracted parameters. So basically, what I did to estimate that is to take all the parameters the same, but just slightly changing the inductance, so they are more in tune with each other to make them perfectly in tune, to have two peaks at the same amplitude, and just compare the frequencies. But it is only to get a rough idea.
Okay. look, what is your confidence that you really see two distinct peaks here? I mean, if you look at the raw data,
yes, I agree.
It's really not obvious that.
Yes, so that's where the question of the error bars are really significant, because I completely agree that with this spectrum, it would be hard to convince anyone that there is a strong coupling. So that's why first we need to repeat the experiment, because if we have better coupling, the result might be more obvious in the raw spectrum. And then, yeah, the results, we could also, I would say, get better at removing the Fabry-Perot effect. I would say by making sure there is really no variation in the substrate thickness and this kind of stuff. So for the moment, I would not. I cannot confidently say, of course, that there is actually splitting here. But I would say that this is not far.
Yeah, there's definitely an interaction between the two resonators. Okay, and I would like to conclude maybe with something we did not talk about during the talk, but it's very nicely explained in the manuscript. It's about optical tweezers. Well, first of all, it's once again very nice experiment. It's very impressive that. I mean, you can derive part of the terahertz gas terahertz relation about the incident power of the laser. Yes. But did you take into account let's say the coupling efficiency of the? I mean, you send in some power, and then the split ring will couple only a very small fraction of it.
Yes. So I think the power that I used for this estimation is 1 milliwatt. And I did not have a precise data on exactly how it would couple. But the actual power that we measured right just outside of the microfluidic cell is 30 milliwatt. So
yeah, but that's not necessarily the power which couples inside the.
No, that's why I took a low estimation for
But
calculating the force.
Given your spectroscopic data with a single split ring, do you think you can go back and reevaluate this?
Yes, there is probably some revelation. For example, with the question of the directivity, I did not have those insights when I did this experiment, so that could clearly be re-optimized now.
Okay, thank you. Well, I have many other questions, but I will leave the space to, and also because this is really extraordinary and very interesting work. So, thank you very much.
So thank you, Janko. So now I will give the floor to the jury member. So perhaps we can start with Giacomo, if you want to have some discussion on the work and question.
Thank you. I'm not more far because I think Peter is more far than me, but I accept for the moment to take the word, and I would just join Janko and also Oleg to congratulate Theo for the very nice work. I sort of browsed the thesis, more than browsed, I didn't really read it like someone who has to write a report would have done, but then I followed the presentation. It was extremely nice, well crafted, very interesting data. The topic is very close to my heart, as you know, so really very well done. A lot of the questions have already been asked because they have been fired, but I still have something to ask. Let's start from the single resonator measurement. Janko was already mentioning this asymmetry in the line, right? That you have, that can be attributed to the multi-reflection. One thing I noticed in the figure that you have at page 85 of your thesis, where you basically compare the transmission spectrum of the single with a fit.
that you have here, I see the asymmetry, and if I look at the figures of chapter 1 where you reported the typical measurement, I don't see the asymmetry, maybe because there is not the effect of the substrate. I was just comparing with some of the figures you have in the first chapter. The thesis, not to the presentation.
But I have in the first chapter some measurements that are pretty similar to the one on the left here. So
the measurement. No, I was talking about the simulations.
Yes, this is a simulation.
Yes, it's true. Yes. Okay, you're right. Then it's this is the one normalizing the. Well, sorry, I looked at one simulation without the substrate transmission.
Okay.
It's the one at page 15, where there is a very nice symmetric line. But anyway, so this is solved. Another question that I had, I mean, this is more of a curiosity / suggestion, but on the part where you do your scanning probe measurement of the resonator. So, have you ever tried, or would it be possible in your system to excite in one place and detect in another place? You know
yes.
What I mean? And you pump a nearby resonator, but you scatter the light out of another one.
Oh, I see.
We investigate the coupling of because these resonators, as you said, if it's an array, they will diffract.
Yes.
And they will talk to each other, let's say, so to speak, with this also in plane radiation. If it would be possible to excite in one point and scatter out in another, if there is enough signal.
I guess it could be technically possible. Now, we didn't do that, but we did try to compare the measurement on a split ring resonator that were in an array and compare them to isolated resonator. And there was no difference in the images. So we concluded that this effect was not predominant in our image. And yeah, we could not see any difference.
But you agree that when you measure with a far field setup, the transmission of let's say of an array meta surface and the transmission of the single one, as you very nicely did, you see differences in the spectrum, right?
Yes.
So this is something that cannot directly be reconnected to the field distribution of the single resonator that you are imaging, right? That's what you're saying.
Yeah, I think.
Okay. So at that level, you don't see any difference. One quick question about the measurement. You said you normally for the very high signal to noise measurement, you have 10,000 traces. This is in terms of time, how much?
For my measurement, it's 25 minutes.
25 minutes of time, okay, for one trace.
Yes.
And it is like independent from, because you reported resonators at quite widely spaced frequencies, which is very nice. So this was basically independent from the frequency, or when you were at, let's say, sub 500 gigahertz, you had to integrate more, or?
No, the parameters were always the same. In the measurement that I showed, it's always the same. Now, for the most conveniently placed one, for example, at 1 terahertz, we could get a clear spectrum at only 1,000 averaging. But I took 10,000 for all of them.
Already there. Okay, and then I had another. Okay, maybe I missed it, but you have this fantastic resonator with a super narrow gap. Do you have the measurement of that one?
No. This one was made in an array, and we did not come back to it once we were able to measure single split ring resonator. So we were first focused on extracting, knowing if you could extract information, and then the plan is to go again toward lower gaps. small.
So is it in an array in the sense that you have an array where all the resonators are sort of with this narrow gap within some error bar?
Yes.
Okay, so it's pretty homogeneous, this thing. You manage to have this kind of 20 nanometer, the next one is going to be 30 or 32 or 35, something like this, or even less?
Probably some of them were close, actually, but yeah, it's hard to say for sure. It was just about testing how low we could get.
Yeah, but you measured, I guess, this array in transmission just to get the resonance.
Yes, I believe we did. Yeah, and
There was
yeah,
nothing special, let's say. It was just the right frequency and that's it.
Yes, basically.
Okay, okay, I see. And so, in terms of the outlook for your let's say coupling to different kinds of substances that you can now, you proved you can do it on the single resonator. What would be the next thing you would like to test or to try there?
So yeah, first of all, going to single crystals, then removing everything that's around, and then for other material, this is where it could be interesting to go lower in size. So to tackle stuff like proteins and maybe get as low as few proteins as possible inside the gap.
But still, I mean, you want to keep your track of, let's say, broadly speaking, biologically related sample and not to place there sort of something like a color center in diamond or whatever, another sort of easy to level system where you can study it a bit for some aspects of it in a bit easier way.
Yeah, that would be interesting for sure.
Sorry, I'm just browsing again my little notes that I have on your thesis. But okay, this has been asked already. Okay, one thing that I wanted to ask you, maybe it's written in the thesis, but still I didn't look at it. Why is the spot of your gas laser when you focus onto the sample and you do the scattering experiment? Or if you have an estimate of why this is?
So I don't have the exact number of the numerical aperture in mind. I think it's in the order of 100 micrometer.
Okay. So it's really 2.5 terahertz is what to 120 microns, so you are very close. I mean, you did a good job in making a small spot. Okay. Okay, and you never consider, basically just because of your lab availability, because you said at the beginning in the introduction that most of the terahertz sources are very low power, the QCL people have demonstrated at some point, even with Terrace QCL, you can have 100 milliwatts, or some people even made watts in the Terrace QCS. But let's say watts is very special, but I think 50 milliwatt you could have if you ask some nearby labs. So maybe it was spectroscopy in a wider range of frequency, you could have that. Okay.
Yeah.
But in general, it was a super nice work. So congratulations, and from my side, and for the moment, I am okay.
Yep.
Okay, thank you. So now I will give the floor to Peter Kyung for discussion and question.
First, I would like to congratulate you. It's really nice results, and you did a very good presentation. And also, I really enjoyed reading your thesis. So I have, I guess, a few additional questions about the part where you try to investigate the glutamic acid coupling to the single terahertz resonator. First, I would like to ask, so in your basically your thesis and also the presentation, you assumed that the glutamic acid crystal is mostly just above the single resonator, right? It's not inside the gap.
Yes.
Inside has the gap. So what is the? Have you done some factorization so that you came up with this conclusion, or is it more like a guess?
It's mostly a guess that comes from the fact that the crystals are mostly flat, and so it would be much better if it could be also inside the gap. It's just that with our capabilities, assuming we have a nice single crystals, it would just be, the plan was to put it on it. Now, of course, in this image, it's probably not the case, but that's one of the reasons why I prefer to have a thinner splitting resonator. So I lose a bit of quality factor, and I add some internal losses because of that. But the thinner it is, the more I can neglect anyway the capacitance of just inside the gap. Like if it's thin enough, all the capacitance is already around and not directly inside. So yeah, but it's, in any case, that would be very useful to characterize more precisely how is the coupling really. So, but yeah, for this experiment in particular, we could not do it.
Yeah, I asked this question is because based on our experience, I would actually be surprised if there is not much glutamic acid inside the gap, because what the geometry of this gap, a few hundred nanometer wide, a few hundred nanometer deep, right, and also a few hundred nanometer in length. I think it's very similar to basically so-called nano trench that we previously used to actually trap molecules in the gap. If you think about the evaporation process, right, the liquid, if it actually infiltrates into the gap, that liquid will be actually the last to evaporate. So therefore, it will have some, basically molecules that are precipitated inside the gap. So that's why, I was wondering why you assumed that there's not much in the gap.
Yes.
And another question related to this is that in your thesis, you showed the transmission measurements of the basically palette of this amino acid, right, which you observed a molecular absorption mode at 1.2 terahertz, as well as two additional lines around 2 terahertz. And then later you also characterized the transmission of these precipitated crystals on the substrate. And in that measurement, you show that there is a relatively strong peak, but a single peak at 2 terahertz.
Yes.
And there's no observed mode or absorption line at 1.2 terahertz, right? So, and then you discuss why this is different from the measurement of from the bulk material, right, from the palette. And one thing you mentioned is that one possible reason is that maybe there's the crystal structure is different, right, from the palette. Right? But then you also said that it's unlikely this is the case. But my question is, or maybe it's a comment, is that I think it's actually a very likely cause, because this kind of amino acid, they have multiple polymorphs. I don't know how many polymorphs the glutamic acid has. Some of them have 5 or even more.
Yeah.
And also, it's very likely when you have these recrystallization or precipitation, different polymorphs form. It's very sensitive to the environment, for example, the substrate, as well as the drying conditions. So I think it's actually quite likely.
I did look into the different polymorphs, and it appears that there is mainly 2 of them. And the one I'm interested in, the one that has the resonance of at 1.2 terahertz, is the easiest one to get. So there is some publication on how to get the other one. And it appears that at room temperature, and yeah, in this kind of situation, you will very mostly have these polymorphs, and you need to do quite some effort to manage to get the other ones. So that's why that's another advantage of this material. Is that
you see this one you chose because it's actually difficult to get the other polymorph?
First of all, and the other one doesn't have a resonance at 1.2 terahertz.
Right, I understand. I mean, usually these different polymorphs have actually very different spectra in the terahertz.
Yeah.
But at least for some MNSs, I know that's actually not difficult to get the different polymorphs. It's really very sensitive.
Yes.
But if you just look at the transmission spectrum for the this crystals on the substrate that you measure,
Yes.
even at the 2 terahertz, you only observe a relatively broad peak instead of 2 relatively narrow lines, right? So I think even from the 2 terahertz, it suggests it might be a different polymorph. And also the fact that you don't see the absorption line at 1.2 terahertz. And I think all combined, I think once you make sure this is really also to see what exactly this is, I think you can do an X-ray diffraction to actually see the crystal structure.
Yeah. So actually, with this amount of glutamic acid, in the beginning, I was not expecting, without the splittering, I was not expecting to have any signal at all, and I was so what we get at 2 terahertz is hard to. You cannot really extract a really line width. It's just what you can only see is a broad modification of the Fabry-Perot because there is some reflection. So what you see reappear, if you look at the line width, it's just the line width of the Fabry-Perot itself. It's hard to deduce what the line width of the absorption is, and yeah, if you look at 2 terahertz for 150 micrometer, the interference are very favorable while they are completely defavorable at 1.3. And actually here I cut the spectrum at 2, but in fact I have some. Here you can see that so it's light, but you can still see even in this measurement a slight you constantly have this peak that is lower than the other one just at 2 terahertz, and yeah, you can only see the thickness, the line width of the Fabry-Perot, not of the glutamic itself.
Okay, so basically you're saying that the measurement itself from the crystals on the substrate is not really, so basically that's not the absorption lines of the material itself. Okay, it's just a modulation of the Fabry-Perot mode.
Yes. And this is something I would like to get rid of. Right?
Yeah. So the new data that you showed in this presentation, which is not in the thesis. I mean, one I think the obvious change is that in this case you have a much stronger resonance from the resonator, right, compared to the one that you showed in the thesis with the glutamic acid on it. So what was the improvement that led to this better results?
So the biggest difference is the thickness of the substrate, because as I said, on the 150 micrometer, which was our first substrate, the interference from the Fabry-Perot are completely destructive at 1.2, 1.3 terahertz, and so this strongly decreases the efficiency of the coupling between the far field and the split ring. So what we did here is to switch to 1 millimeter thick substrate. On the spectrum themselves, it looks it can look worse than before, but actually with this thickness, So first of all, we can separate the pulses. So it's possible to filter and to get an idea of what's from the interference and what is not, but I didn't show that because there is not enough resolution to really extract much. And actually, since the variation in thickness is taken into account in the models, even though visually it looks more difficult to interpret, it doesn't disturb that much the extraction process. Now, of course, to get something more convincing, we will soon investigate the possibility to use some anti-reflecting coating and get a way to really reduce the reflection, so to have something that is we are both able to fit and that is more convincing.
Okay, all right, great. That's all my questions.
Okay, thank you. So before giving the floor to the supervisors, I will have a few questions also. So not so much because there are so many. And so first I want to join the congratulations for your talk, your presentation, which was really clear, and also for all the work. And it's quite impressive, so many instrumentation you have developed, and which was really hard experimental stuff. And you, at the end, the results are very nice and interesting. So congratulations for that. And so now I have a few questions. So the first one is related to this RLC model. In fact, I understand that it raised the question of the high quality factor compared to the theory of couple modes. Mm-hmm. But I was wondering if there is another advantages to use this model in case of you have a sufficiently high quality factor in your system.
The main motivation is to have a clear link between the capacitance and the final formula. So even though I expressed it in both ways in the presentation, in the thesis, you can see that I can express everything just in terms of the physical value and have the C. So for the moment, I could just say that the resonance frequency is inversely proportional to C, and do the same with coupled mode theory. But this is something that I will not be able to do as soon as I refine a bit the model. So, for example, let's say I want to use the split ring to probe the permeability of an object. Then the inductance will be changed, and you can see in this formula that it interacts with most of the parameters. And yeah, it's better to keep in mind how each values in the time domain coupled mode theory are linked to the physics of, and how they are linked to what I want to measure. So it was to clarify this point mostly, and also to evaluate the importance and the impact of all the hypotheses that are done for coupled mode theory, which is only valid for high quality factor. And there is no reason to assume that I will only have high quality factor in this case, especially if I try to couple the split ring with material that has high losses. I will immediately go out of this range of validity.
Okay, so another question is, could you compare all the gain you get on signal to noise ratio using your technique with your 10,000 scan compared to if you were using a measurement which is quite usual with a locking and a long time constant? So a long time integration, so less scan, less average, but an integration for each position of the delay line?
Yes, the main problem with that would be, I guess, the delay drift. Because the question would be, would you still have this kind of drift? And if you do, can you correct it? Here, this drift is quite slow. It's on the order of magnitude of several minutes. So it's easy to correct because I can assume that for one single trace, it's the same for every point in the trace. If now I take this time 25 minutes to get a single trace, this will, if we still have this kind of drift, it will change along the time trace, and this will be much more difficult to correct.
Mm-hmm. Okay. So did you consider for your single measurement, so your measurement on single split ring resonator, did you consider to couple it with a Fabry-Perot cavity as it has been done in another group?
I would say that the substrate itself is a Fabry-Perot cavity, yes. and without particularly wanting it, I had some coupling with this cavity. Yes, so in this measurement, except for this one, all the other ones were taken at a frequency where the interference from the cavity was highly favorable. So it happens to be not on purpose, but it is the case. And so actually it clearly showed that this coupling can really help to detect the resonator. So the first thing I did was to increase for the moment the thickness, just to be sure that there is at some frequency a favorable coupling. But it could be also interesting instead of doing as thick as possible to get something that is specially tuned for the frequency I want to measure. So here I guess that would be around a substrate of slightly larger, just to shift the peaks at 1.3, and we could have had nice results that were maybe probably easier to interpret thanks to the coupling with the Fabry-Perot cavity.
Yes, then you can have several substrates also to do distributed Bragg reflector.
If you want to tune as much as possible the coupling. Yeah.
And so my last question is for the measurement with the glutamic acid. So what you show us is the transmission in amplitude. Mm-hmm. And did you look at the phase and if there is a feature which can be used to probe the acid?
The phase is, well, as you can see from this measurement, between the reference and the measurement, there is some, well, the fact that the Fabry-Perot is kind of coming back at high frequency is a sign that there is some inconsistency in the thickness of the substrate, and so this is mostly what you see in the phase. You have a strong slope because of that, and it's actually quite hard to get interesting features for the moment. But we would need to improve a bit more and about the validity of the reference.
Okay, thank you. So I will give. So Oleg, do you want to ask one or two questions more because you asked for?
Yeah.
Okay.
Yeah, absolutely. Thank you. And actually, I'd like to mention that listening to your answers to other questions, I'm very satisfied the way you technically very comfortable in discussing your data, you very discussing your models. So I don't necessarily want to spend time going into the technical details, but I do want to ask a couple of questions that are more of kind of your outlook sort of vision. Having done all these experiments, and imagine there's not many people in our community who has the knowledge that you have now. I wonder if you could come back to the original question that you started your studies with. So let's say you have this a very small object that you'd like to investigate in terahertz frequencies. And you discussed several approaches in your studies, let's say taking a resonator, or, for example, now you also have the knowledge of, in principle, you could take this scattering snow system and, as we actually just discussed earlier in one of the questions, you could, in principle, just put the tip on top of the resonator and try to run the TDS. So there are a couple of solutions to do this, but obviously none of the solutions are straightforward and simple. So having done all these studies, what would be your suggestion to other researchers? Like, what do we do? Let's say you have a very small object and you want to do terahertz spectroscopy on it. What is the right way to do it in terahertz frequencies?
I would say that first you have to know a bit what you are looking for. So I would suggest starting with some vibrational simulation to get a rough estimation of the precise where you expect to see features. Yeah, I guess I would start with near field imaging. That would give insight in well, basically, is there something happening or not with this material in your targeted frequency range? And yeah, if there is, then switch to a method like that. I think it would be interesting to, with this kind of setup here, I only showed an extraction. In the case where I had already in mind a model, I knew I wanted to fit it with the Lorentzian model. Of course, with a completely unknown particle, that would not be the case. So this technique will need to be a bit adapted to, instead of giving you directly parameters, to give you at least a rough estimation of well, the actual permittivity spectrum. And with this modification, you could get insight into yeah, the overall look of your spectrum, and then you could go back to try actual models, material models, and go back to the original data, and yeah, try to check your hypothesis with that.
So maybe I didn't quite hear your sort of judgment whether should people try to, let's say, do the same thing with putting this object in a split ring resonator and put another resonator and align the resonance to the resonances you expect in the material, or do you think there's a sort of hope to do, say, just do TDS in the S snow configuration by putting the tip on top of your sample?
There is indeed potential. The problem is about the modelization. Here I choose to investigate the split ring resonator well sub-wavelengths because I could easily go back to the RLC circuit, and this is a system that I can model quite confidently, and all the extraction relies on the assumption that my my model, how it behaves, in spectroscopy, are well consistent with the reality, as we saw in the part about SNOM imaging. How to model exactly what we measure in a SNOM system is not at all straightforward. And so I think it would be very difficult, even more than with the split ring, to make a difference between what are the actual features of the material and what comes from an expected behavior of the very, very complex system that is a SNOM microscope.
Okay, thank you. And the second, it's also kind of an outlook type of question. Having done all the studies on the split ring resonator and even proposing there's a different methodology where you would basically rotate the sample in the different angles and basically reconstruct the image. I think this methodology would be fairly difficult to implement on a regular basis, just because we're going to be very time consuming. So, but I think kind of more generally, what I would say, there are several ways people look at, let's say, scattering SNOM, right? And there's got to be some sort of interpretation. What exactly are we seeing? Are we seeing modes of the resonator? Are we seeing material contrast? So having studied your system, particularly in this relatively large tip, which seems to be essential for terahertz studies because of better scattering efficiency. So what would you say if you were to describe to people what exactly you see with the terahertz as SNOM measurements? I know it's a complex question. So
you mean what?
Say, if you were to extract sort of one of the main things that you're observing, what exactly is that physical information?
I guess it's the local density of mode that are coupled, at least efficiently coupled to the system. Now, yeah, but it's difficult to extract what part of that is actual density of mode and what is about the coupling with the system. But that's still the main idea, because you never the consistent the very consistent thing about our measurement is we never have a really strong signal at the point where there is no we never have bright spots outside of the expected resonance.
So you're saying that you do have information about the mode, but it's just a little bit becoming a little bit convoluted because of this scattering modification of the sort of angular distribution of the scattered signal. And okay, and then just maybe the last thing. So with the modification of this angular distribution, I guess you also may expect that effectively now your resonator is not just a resonator, it's a resonator with a metallic stick over it. Can we say that the spectral properties are more or less the same, or the system was modified so much by this tip that you could say, wow, now it doesn't really behave like maybe the resonance frequency shifts. So can you, what's your sort of assessment? Can we still apply this technique and say, okay, we are actually investigating this individual resonator?
We tried that in simulation, see how much the tip would disturb the system, and we do detect some shift in the resonance frequency with or without a metallic tip, but it's quite negligible compared to the line width of the resonance. So overall, the effect on the resonance on the spectrum itself is much lower than what we could expect, especially if we look at the difference in sizes. But in terms of capacitance, there is not so much coupling. It doesn't disturb that much the resonance.
Okay. All right. Thank you. No, this was also very, very useful. Thank you. Thank you.
Thank you, Oleg. So now it's time for supervisor who wants to start. Okay.
So yeah, I want to thank Theo for this almost 5 years now. I mean, you began in something like February, March, maybe April. 5 years ago. Yeah, it was a quite long journey with COVID, with a 1 year in US during COVID, with a lot of results, with a lot of problems, with a lot of solutions, and yeah, a lot remains to do. So it's excellent foundation for the future. Yeah, I mean, everybody say what they say, but what they thought about your pedagogic presentation, your manuscript. I don't have much to add. I was really happy to work with you, and I hope to continue in the future.
Thank you, Romain. So, Jean-François.
Thank you very much. So I will not be very long also. I will not have questions because we have we have a lot of time to discuss about the different results you obtained. So I must say that yeah, it was a pleasure to participate to the direction of your thesis along these years. As we have said, you are quite rigorous, and particularly for the experiments, and that's really a pleasure. It's not always the case nowadays, but in your case, it's the case. We have seen also that you are able to manipulate quite easily the numerical tools and to try to do comparison with experiment, come back to the simulation, come back to experiment, and to really improve your results using both. And it's really also something very important for me. And also, you are always in good mood, and always going to try new things and to go further in your experiment. Concerning the experiment, there was, as it was mentioned before, there was several experimental setups, in fact. So for the optical tweezer, you have almost done everything yourself. Concerning the TDS, also you participate a lot to the improvement of the setup, even if it's a commercial, at the beginning it's a commercial setup, but you have shown that it can be really improved compared to what you get when you simply buy it. And concerning the SNOM, so yeah, we obtained very good results. I must mention that you had the help from Louis Thomas and also Christian Nascimento Santos during this very long and time-consuming experiment and years of improving the setup. And so I thank them also for their very good work on this scattering SNOM experiment. And also the company vMicro, who has developed these long tips that were really essential to get sufficient signal-noise ratio for this difficult experiment. So that's all. Just as Romain mentioned, we must mention that there was the COVID during your thesis, and it was not so easy during this period, but now we can see that, in fact, it didn't impact too much I must say, your thesis at the end. Okay, so that's all for me.
Will you talk about the next meeting? The link?
Yeah. So for Oleg, Peter, and Giacomo, so I send you an email for the meeting we have just after the questions.
Okay, so thank you. And so it's time for the deliberation. So we move, that's right?
Yes.
We move in the another room. Okay, thank you. Après la délibération, donc le jury vous délivre le titre de docteur en électronique et photonique de l'Université de Lille. Tous les membres du jury vous félicitent pour ce travail très impressionnant, cette soutenance très pédagogique, très claire et votre capacité remarquable à répondre à toutes les questions très techniques sur un domaine très large d'expertise. Donc voilà, on est très contents de tous te féliciter pour tout ça.
Merci beaucoup, merci. Merci à toutes les personnes qui sont venues et qui m'ont soutenu pendant tout ce temps. Et ça a été plus long que prévu, on va dire. C'est avec beaucoup de rebondissements. Et puis, ce qui fait que je suis arrivé en même temps que beaucoup d'autres et je repars après, mais, mais ils sont revenus. Donc, merci, merci tout le monde, merci à l'équipe technique. Et, voilà.
Merci Théo.
Allez, félicitations. Bravo.
Félicitations.
Félicitations.
Ah oui, oui, pardon, oui, c'est vrai. Et je vous invite maintenant à rejoindre la salle Pierre Armand pour en discuter, pour délibérer de cet événement.
Pour la suite des discussions scientifiques.
Oui, exactement.
Pour participer ensemble.